Hello everyone, my name is Joel Fernandis. I am from Creative PU College, Karkala. Today we will discuss some questions related to kinetic theory of gases and thermodynamics. Let's move on to the first question. Okay, the first question says that the temperature at which the mean kinetic energy of oxygen molecule will be the same for H2 molecules at minus 73 degrees Celsius. So you can see there is a hydrogen molecule, and this hydrogen molecule is at a minus 73 degrees Celsius. And what the question says is, you have to find the temperature at which the oxygen molecule also will have the same kinetic energy as that of a hydrogen at a minus 73 degrees Celsius. We all know that the mean kinetic energy of any molecule, doesn't matter what type of gas it is, for any molecule, the mean kinetic energy is given as a 3 by 2 kb into T, where kb is nothing but a Boltzmann constant and T is just a temperature. So if you look at this, 3, 2 and kb, all are constant. So mean kinetic energy depends only on temperature, nothing else. So the temperature of oxygen molecule also will be minus 73 degrees Celsius. That gives us the correct option as a option C. Let's move on to the next question. So next question says, when the temperature of the gas is raised from 27 degrees Celsius to 90 degrees Celsius, the percentage increase in the RMS velocity of the molecules will be. So let's find out what's the formula for RMS velocity. So we have a RMS velocity given as a root of 3RT divided by m naught, where m naught is nothing but a molar mass. T is the temperature and R is a universal gas constant. So we can see from here that this RMS velocity is proportional to only root of temperature. Other terms being constant for a given gas, RMS velocity varies only directly with the root of temperatures. So let's take the ratio. So V2 divided by V1, this will be equal to root of T2 divided by T1. Now let's find out what is the final velocity. So we can find out here root of, so final initial temperature is given as a 27 degrees Celsius. So this formula works only if the values are substituted in Kelvin. In degrees Celsius, this formula doesn't work. So to convert this 27 degrees Celsius to Kelvin, we have to add 273 to this. So when we add 273 to this, it becomes 300 Kelvin. Similarly, the final temperature is given as a 90 degrees Celsius. So we have to add 273 to this. So when we add 273 to this, it becomes a 363. So this comes under root. We get root of 1.21, and root of 1.21 is equal to root of, it's like taking root of 121. Root of 121 is 11. Similarly, root of 1.21 will be 1.1. So we can write this V2 is equal to 1.1 times V1. So if I convert this answer into percentage, so 1.1 is equal to 110%. 110% of V1. That means there is an increase of 10%. So the correct answer will be option A. So there is an increase in 10% of the final RMS velocity. Okay, now let's move on to the next question. Question number 3. Okay, the question says there are two spherical vessels of equal volume. They are connected by a narrow tube. The apparatus contains an ideal gas at 1 atmosphere and 300 Kelvin. Now one of the vessel is immersed in a bath of constant temperature 600 Kelvin and other in a bath of constant temperature 300 Kelvin. Then the common pressure will be. Some options are given. Now let's just look at this diagram once again. So there are two vessels. So I will assume that this vessel, this is at a initially both are at a 300 Kelvin. So finally, after some time, this is kept at a 300 Kelvin. The second one is kept at a 600 Kelvin. But if you look at this diagram, so there are two vessels, and they're connected using a pipe, but everything is concealed. So there is no escaping of the gas molecules outside the system, and there is no gas enters into the system. That means the total number of molecules present inside this is a constant. So since total number of molecules are constant. So I'll write total number of molecules before changing the temperature is same as the total number of molecules after changing the temperature. So let me take volume of this was V, volume of this also as a V. So let me use the ideal gas equation. So when I use ideal gas equation, we have PV is equal to mu R T. So the number of moles can be written as a PV divided by RT. So this is the ideal gas equation. Now let's use this ideal gas equation in the beginning. So in the beginning, it's given in the question that the pressure of entire system is nothing but some P that is written here, but initial volume is of container A and container B. Total it becomes 2V. V plus V becomes 2V, and R is anyway universal gas constant, and entire system initially at a temperature T1. But finally, after changing the temperature to 300 Kelvin and 600 Kelvin, in the first container, the pressure changes to some P dash. We don't know how much, I've just written it as a P dash, but volume of both containers still remain the same. So here V, RT1, similarly, the pressure in the second container, B also becomes a P dash, volume remains the same, RT2. So let's solve this. Here V cancels everywhere. So after cancelling V, remaining is only here 2P RT1. So P dash you can take common. So if you take P dash common, I will write one step here. So 2P divided by RT1. This is equal to, I'll take P dash and R common. Remaining will be 1 by T1 plus 1 by T2. So take the common LCM. So this R is going to cancel out. So remaining is 2P divided by T1. That is equal to P dash. Then take the common LCM. That will become T1, T2. And numerator will become T1 plus T2. Now rearrange the equation. So once we rearrange the equation, we are going to get this equation. So finally, take all these quantities to the other side. So we get final pressure as a P dash is equal to 2 times P T2 divided by T1 plus T2. Now let's substitute all the given values. So initial pressure is given as a 1 atmosphere. Final temperature here is given as a 600 Kelvin in the second container. In the first container, the final temperature is given as a 300 Kelvin. Once again, the temperature of the second container as a 600 Kelvin. So if we solve this, we are going to get option, I think option C, it is option, it's 4 by 3 atmosphere. 4. So pressure versus temperature graphs of an ideal gas are as shown in the figure. Choose the wrong statement. You have to identify which statement is wrong. You have to identify the wrong statement here. Now look at the given graphs. So given graphs are pressure versus temperature graphs. All the 3 graphs are given as a pressure versus temperature graphs. But look at the options. So first option says density of the gas is increasing in graph 1. So given graph is pressure versus temperature graph, but the options, all the options are talking about density. So somehow we have to convert this pressure versus temperature information into density information. So let's just look at the first graph. So let me use the ideal gas equation. So according to ideal gas equation, you can write PV is equal to mu R T. So pressure, here you can write this as a mass divided by density. Volume can be replaced as a mass by density. On the other side, number of moles can be written as a mass divided by molar mass into RT. So let me rearrange. So density can be written as a P into m naught divided by R into T. Now look at the first graph. Look at the first graph. So in the first graph, temperature is constant, but pressure is increasing. Temperature is constant, pressure is increasing. So since pressure is increasing, density is also increasing. That means the first statement is a right statement. Look at the second graph. So pressure is kept constant, but temperature is going on increasing. So pressure is constant, so temperature is going on increasing. Anyway, other quantities m naught and r are constant for a given gas. So since pressure is constant and temperature is going on increasing, density will go on decreasing. So the second says density of the gas decreasing in the graph 2. So second statement is also correct. Now we have to identify what's going to happen in the third. Now if you look at this graph, so here there is a linear relation between pressure and temperature. But if you look at this graph, it is not coming from the origin. It is going to cut this pressure axis somewhere here. So let me call this value as some A. So I can write the equation of the straight line. Let's write the equation of the straight line. So pressure, this can be written as a some A plus some Bt. But according to ideal gas equation, I'll assume that the number of moles are just 1. So in place of pressure, you just write as a RT divided by V. That is equal to A plus Vt. So since we want density, and density is directly related to volume, I'll write this equation in terms of volume. So I'll take V to the other side. So RT divided by A plus Vt. This becomes equal to V. Now let me take this T downwards. So R divided by will become A by T plus V equal to. Now this is the equation of the volume. Now see here. In this graph, temperature is going on increasing. So as the temperature increases, this entire denominator goes on decreasing. So here, temperature is going on increasing, entire denominator goes on decreasing. So this, the value on the left hand side, this value will increase. The value will increase. So volume is going to increase. If the volume is going to increase, the density is going to decrease. But the question option C says that density is constant. So this is a wrong statement. That gives us the correct option as a option C. We have to identify the wrong statement. And in this statement, volume is, according to this statement, volume is constant, density is constant, but we proved that volume is going to increase, and as a result, density is going to change. So hence, option C will be the right option. Let's go to question number 5. The energy of a gas per liter is 300 joules. Then its pressure will be. Now let's use the relation between pressure, volume, and energy. So we know PV can be written equal to 2 by 3E. So let me take V to the other side. So pressure is going to become equal to 2/3 E divided by V. 2/3 of E by V. Now this E by V quantity is given. Look at the given information. It is gas per liter. Energy per liter is given as a 300. But let's substitute. So in place of 2 as it is, in place of this energy per volume, I'm substituting 3 into 10 to the power 3. That is given here, 300 joule divided by 3. So finally, we will end up with the answer 2 into 10 to the power 5 Newton per meter square. And why there is a 10 to the power 3 here? It is given per liter. Per liter. So 1 liter can be written equal to 10 to the power 10 to the power minus 3 meter cube. So when it comes to the numerator, it becomes a 10 to the power plus 3. So that's why there's a plus 3. So finally, 2 into 10 to the power 5 Newton per meter square is the option. That gives us the option D as a right option. If the degree of freedom of a gas is F, then the ratio of two specific heats, so Cp by Cv, is given by. So we know the relation between Cp and Cv. So according to Mayer's equation, Cp can be written as a Cv plus R, and Cv is also nothing but F by 2R. So let's substitute and let's find out the ratio. So this ratio, gamma is asked, so that is nothing but Cp divided by Cv. So Cp can be written as a Cv plus R divided by Cv is nothing but F by 2 R. So let me write one more step before this. So this is Cv plus R divided by Cv. So Cv by Cv is going to become 1 plus R by Cv. So this is going to become 1 plus R by Cv is already nothing but F by 2R. So R and R is going to cancel. So finally we get gamma is equal to 1 plus 2 by F. So that is option A. Okay, now let's solve question number 7. So for a gas, R by CV value is given as a 0.67. And this gas is made up of molecules which are, you have to identify which type of molecules are present in this graph, in this gas. So R by CV value is given. So we have some relation. We can write gamma, that is the ratio of specific heats. That is gamma is nothing but Cp by Cv. So gamma can be written as a R by 1 plus R by Cv. So R by Cv value is already present here. So that if I substitute 1 plus 0.67, so it becomes a 1.67. So when we look at the value of gamma, we can identify what type of gas is present here. So let me show one table. Now look at the table. These are some properties of the gas of different types of gases. And if you look at this, 1.67 gamma value is for monatomic gas. So hence the gas will be monatomic gas. And you can see for diatomic and polyatomic gases, different values of Cp, Cv, and gamma are given here. Okay, let's solve question number 8. The pressure exerted by the gas on the walls of the container because. So we already know, according to the postulates of kinetic theory of gases, so when the molecules move, when the molecules move of an ideal gas, they hit the walls of the container. And when they hit the walls of the container, they exert some pressure on the wall. So on this pressure, on this container, there is a wall here. And on this wall, this molecule will go and hit it. When it hits, it will exert some momentum on this. And because of that, collision, the gas molecule is going to rebound, and we assume that at this place the collision that is going to take place is a elastic collision, and since it is an elastic collision, it is going to rebound with the same momentum. But because of this change in momentum, there is going to be some force exerted on this, so that gives us the option C as a correct option. Let's solve question number 9. So which of the following graphs correctly represents the variation of beta is equal to minus 1 by V dV by dP? So we have a given equation, beta is equal to minus 1 by V dV divided by dP. So let me take this equation as equation number 1. Now look at the given information. This question says there is a gas at a constant temperature. It's a constant temperature. That means the process is a isothermal process. It's an isothermal process. And for isothermal process, we know PV is a constant. So let's differentiate this equation. P into dV, that is plus, we have V dP, that is equal to 0. So let me rearrange and let me write this in this form. So let me take this term to the other side. So V dP is going to become equal to minus P dV. So we have a term dV by dP. So I will take dP to the other side. So V is going to become equal to minus P dV divided by dP. So let me take volume to the other side, pressure to the left hand side. So minus 1 by P is going to become equal to 1 by V. Here we have dV divided by dP. So let me write the minus sign this side because it's given in the equation 1. Now let me take this as a equation 2. Now compare equation 1 and 2. Left hand side is beta, here left hand side is 1 by P. So this implies that beta is simply nothing but 1 by P. So we have a relation between beta and P. So if you look at all the graphs, here the graphs are plotted between beta and pressure. And we have the relation between beta and pressure. So they are inversely proportional. So this graph is a hyperbola. It's a rectangular hyperbolic graph. That gives a option A as a correct option. Okay, let's solve question number 10. So PV versus T graph of equal masses of hydrogen, helium, and oxygen is shown in the figure. So there are three types of gases and they undergo some changes, and those changes are represented in a single plot where along y-axis there is a PV and along x-axis there is a temperature. So whenever straight lines are involved, we'll go for slopes. So we have to identify which gas is represented by which of these alphabetically shown straight lines. So let's find out the slope first. So slope is simply y quantity by x quantity, that is PV by T. So in place of PV, so how I obtain this is, in place of P, you can simply write number of moles into R into T. So T and T is going to cancel. So finally remaining is mass by, let me show you the step. So slope. So slope simply PV divided by T. So in place of P, I will write mu RT divided by T. So T and T is going to cancel out. So in place of mu, that is number of moles, I will write mass divided by molar mass into R. That is nothing but a slope. So here slope will be now proportional to 1 divided by molar mass, because masses of all gases are given same, whether H2, whether helium or O2, all of them have same mass. So only difference is molar mass. So if the molar mass is more, the slope should be less. So if you look at the straight lines, A has a minimum slope. So if A has a minimum slope, its molar must be maximum. So that should correspond to O2. Similarly, the line C has a maximum slope. If slope is maximum, molar mass should be minimum. So this should correspond to H2 and the other one should correspond to helium. So that gives the option D as a right option. One small correction is required here. So B, this should correspond to helium and this should correspond to hydrogen, C, H2. Okay, let's solve question number 11. It says that the ratio of specific heat of a mixture of 1 mole of helium and 1 mole of hydrogen gas will be. So we know gamma. Gamma is nothing but ratio of a specific heat. It's a mixture. So we have to write it as a Cp of the mixture divided by Cv of the mixture. Let me take it as a equation 1. So one by one we'll find out. So let me first find out Cv. Cv of the mixture. So Cv of the mixture can be written as a mu1 Cv1 plus mu2 Cv2 divided by mu1 plus mu2. Similarly, Cp of the mixture, this is equal to mu1 Cp1 plus mu2 Cp2 divided by mu1 plus mu2. If I substitute this in equation 1, mu1 plus mu2 and mu1 plus mu2 is going to cancel out. So this equation is going to become only mu1 Cp1 plus mu2 Cp2 divided by mu1 Cv1 plus mu2 Cv2. And given that all the gases have only 1 mole of gases, so this is 1 into, in the table shown for one of the previous questions, we already know what is the Cp value. Look at the first gas. The first gas is a helium. So helium is a monatomic gas. And look at the second gas. It is given as a hydrogen, and hydrogen is a diatomic gas. So let's substitute what is Cp1. Cp for monatomic gas is 5 by 2 R plus number of moles of the second one, 1 plus, so into Cp2, that is a diatomic gas. For diatomic gas, Cp is a 7 by 2 R. Similarly, divided by mu1 is number of moles is 1, Cv1 is 3 by 2 R plus 1 into Cv for the diatomic gas is 5 by 2 R. So if you solve this, we are going to end up, so this anyway 2 is going to cancel out. So 5 plus 7 will be 12, and R is also going to cancel out, divided by 3 plus 5 will be 8. So 12 by 8 will give us, so 12 by 8, let's solve that. It will go in 4. This goes 3 times, this go to 2 times. So 3 divided by 2. So 3 by 2 is equal to 1.5. So we have 1.5 as a option B. Okay. Let's solve question number 12. So the RMS speed of a group of 7 gas molecules having speeds 6, 4, 2, 0, -2, -4, and 6 meter per second is. So this minus sign just represents the direction of motion is opposite to the first 3 molecules. So we have the formula for RMS velocity. So RMS velocity is nothing but root of the sum of squares of velocities of individual molecules divided by total number of molecules. So here there are 7 molecules. Let's substitute all the values. So first one is a 6. 6 square is going to become 36. Plus we have second one as a 4. When we square it, it is going to become 6, 16. Plus third is a 2. When we square it, it is going to become 4 plus 0. Similarly, 4 plus 16 plus 36. Entire thing divided by, if you count this, there are total 7 molecules. And you solve this, we are going to get a answer as a 4 meter per second. That is a option D. Okay. Question number 13. In an adiabatic process, 90 joule of work is done on the gas. The change in internal energy of the gas is asked. So let's use the first thermodynamic equation. First law of thermodynamics, heat supplied to the system is partially utilized to increase the internal energy and to do the work by the gas. Now here, look at the given information. There is a adiabatic process. So if it is adiabatic process, there is no exchange of heat with the surroundings. So this is going to become 0. That is equal to delta U plus delta W. And 90 joule of work is done on the gas. Look at the word here. You have to be very, very careful while substituting. The work is done on the gas. So if work is done on the gas, work done will be negative. So 0 is equal to delta U minus 90. If they had given work done by the gas, then we should substitute this as a plus 90. So finally, we get change in internal energy as a 90 joule. That is a plus 90 joule. That is option B. Question 14. A certain mass of gas at 273 Kelvin is expanded 81 times its volume under adiabatic condition. If the ratio of specific heats, that is gamma, is equal to 1.25 for the gas, then its final temperature is asked. So let's use the adiabatic equation, which contains temperature, that is a given information, temperature, and it is expanded 81 times. That means what is given is a volume. So we have many kinematic equations. We have many equations related to adiabatic process. So out of which we are going to use that equation, which contains temperature as well as a volume. So here, Tv to the power gamma minus 1. So this also implies that T is proportional to 1 by V to the power gamma minus 1. So if you take the ratio, you get T2 by T1 will be equal to V1 by V2 whole to the power gamma minus 1. Let's substitute T2. V1, let me write 1 by, it is expanded 81 times. That means final volume will be 81 times the initial volume. Gamma value is given 1.25 minus 1. You have to find the final temperature, T2, and initial temperature is given as a 273 Kelvin. So this can also be written T2 divided by 273. That's equal to this 1 by 81 1.25 minus 1 is 0.25. So 0.25 can also be written as a 1 by 4. So 1/4 root of 1/4 root of 1/4, this becomes a 1 by 3. 1/4 root of 1 by 81 is 1 by 3. So T2 will be equal to 273 divided by 3. So that will be somewhere around 91 Kelvin. And if you subtract this, T2 is equal to 91 Kelvin minus 273, we are going to end up as a option 2, that is a minus 182 degrees Celsius. Question 15. In the case of diatomic gas, the heat given at constant pressure is that part of energy which is used for the expansion of gas is. So what we have to find out is the ratio of work done to the heat supplied. So how much part of heat supplied is utilized to convert it into work. So let's use the equation. So work done can also be written as a P into delta V. Similarly, the heat supplied at constant pressure can be written as a Cp into delta T. But since the gas is a diatomic gas, the Cp value is a 7 by 2R. So we will substitute, then take the ratio. So delta W divided by delta Q. When we take the ratio, we get only delta T cancel, R cancels, we get a 2 by 7. So 2 by 7 is a option C. Okay. Question number 16. There's an ideal gas which is monatomic gas. It is taken around the cycle ABCDA as shown in the PV diagram. The change in internal energy during the cycle is. Now, if you look at this graph, the cycle is given as the process is given as a cyclic process. The meaning of cyclic process is the gas starts from A, it goes around different states, then finally its state becomes the same as the initial state. So if it is the same as the initial state, then there will be its pressure, volume, temperature, everything becomes the same. So the change in internal energy will be always a 0. So that gives you option D. Right option. Question 17. An ideal gas heat engine operates in a Carnot cycle between 27 degrees Celsius and 127 degrees Celsius. It absorbs 6 kilocalorie at the highest temperature. The amount of heat converted into work is equal to. So let's use the equation of efficiency. So efficiency of any engine, Carnot engine, is given as a work done divided by heat absorbed. So that is also equal to 1 minus T2 by T1, where T2 is nothing but the temperature of the sink and T2 is the temperature of the source. So T2 is always lesser temperature, T1 is always a higher temperature. So if you look at this, this will be T2. You have to add plus 273 here. This is T1. We have to add plus 273. So when we add 1 minus 273, so this becomes W divided by 6, that is equal to 1 minus 273 plus 127, that becomes 400. This becomes a 500. So this is 1 minus 4 by 5. So 1 minus 4 by 5 will be equal to 1 divided by 5. Now take it to the other side. So W can be written as a 6 divided by 5. So 6 by 5 is equal to 1.2. So 1.2 kilocalorie, option C. Question number 18. The internal energy of an ideal gas increases during an isothermal process when the gas is. So most of the time we say that it's isothermal process, temperature remains constant. And since temperature remains constant, internal energy also constant. But there is an exception. There is a possibility that we can change the internal energy even during isothermal process also. But you have to check all possibilities. Now look at the formula for internal energy. It is F by 2 mu RT, where F is called as a number of moles. So here, number of moles can also be written as a number of molecules divided by Avogadro number. Now, finally, we can see that internal energy is directly proportional to the product of number of molecules and temperature. And since the process is given isothermal process, temperature is constant. And since temperature is constant, but only possibility to change the internal energy by increasing the number of molecules. So by that can be done by expanding the gas by adding more molecules to it. That is option number A. Question 19. A diatomic gas is compressed adiabatically. During the process, its a specific heat is. So we have formula for specific heat 1 by m delta Q divided by delta T. And since the process is given adiabatic, this delta Q is a 0. There is no exchange of heat. And since it is 0, the specific heat is also 0. That is option C. Question 20. The first law of thermodynamics is based on. So what the question first law says is, heat supply to the system is partially utilized to change the internal energy, and remaining energy is utilized by the gas to do the work. So the total energy gets converted into two different forms. So hence the correct option is a conservation of energy. Question 21. In a given process for an ideal gas, dW is equal to 0 and dQ is given less than 0 then for the gas. So let's once again use the first law of thermodynamics. We have dQ, this can be done as a du plus dW. du plus dW, and here given dW is equal to 0, this term becomes 0, and dQ is given less than 0. Less than 0 means it is a negative. So if it is negative, du also has become negative. The change in internal energy has become negative. The meaning is that internal energy has decreased. And since internal energy is directly proportional to temperature, change in internal energy is negative, internal energy decrease, that means the temperature is also going to decrease. So that gives the correct option as option A. Question 22. A system goes from A to B through two processes 1 and 2 as shown in the figure. If delta U1 and delta U2 are the changes in internal energies in the process 1 and 2 respectively, then now look at the process here. Process 1 and process 2. For both process 1 and 2, initial conditions as well as the final conditions are same. Both the gases have same initial conditions and both the processes will end up also at a same final conditions. That means the temperature at A for process 1 and 2 is same, and temperature at B for process 1 and 2, that is also same. So if temperatures at A is same for 1 and 2, internal energy is also same here for process 1 and 2. Similarly, internal energy at B is also same at 1 and 2. So since both of them have gone through different paths, but the endpoints are same, their internal energies at the beginning and final also same. That means the change in internal energy in the process 1 and change in internal energy in the process 2 are same. That is option C. Question 23. The volume of an ideal gas is 1 liter and its pressure is equal to 72 centimeter of mercury column. The volume of gas is made 900 cm cube by compressing it isothermally. The stress of the gas will be. Now given the volume as 1 liter. So this 1 liter, this can be written as 1000 cm cube. And the process given here is the isothermal process. So for isothermal process, we have PV is equal to constant. And what is asked in the question is stress. Stress is nothing but change in pressure. Delta P is asked. So to find out delta P, first we need to find out what is the final pressure. So let's use the equation here using isothermal equation. Let's write P1 V1 is equal to P2 V2. So finally we can write P2 is equal to P1 V1 divided by P2. Let's substitute. Initial pressure is given 72 centimeter of mercury. So 72 into initial volume is given 1000 divided by final pressure. Let's solve question number 23. The volume of an ideal gas is 1 liter and its pressure is equal to 72 centimeter of mercury column. The volume of gas is made 900 cm cube by compressing it isothermally, the stress of the gas will be. So what is asked is a stress. Stress is nothing but change in pressure, delta P. This is asked. So delta P is simply P2 minus P1. This quantity we have to find out. And the process here given is a isothermal process. So since it is isothermal process, we can use the equation PV is equal to constant, or you can write P2V2 is equal to P1 V1. Now look at the given information. The initial volume is given as a 1 liter. So 1 liter can also be written as a 1000 cm cube. So let's substitute. Let's find out P2 is equal to P1 V1 divided by V2. So P1 initial pressure is given here, 72 centimeter of mercury column. So 72 into 1000 divided by volume here has become 900. So if I solve this, we will get 80 centimeter of mercury column, but we don't want final pressure, we want change in pressure. So therefore, the stress is nothing but delta P. So delta P is final pressure 80 minus initial pressure 72. So answer will be 8 centimeter of mercury column. That is a option A. Question 24. Two identical samples of a gas are allowed to expand, first isothermally and second adiabatically. Work done is. So we have a slope in case of isothermal process. Slope is nothing but P divided by V, and slope of the PV graph, in adiabatic process is nothing but minus gamma times P by V. And if we compare both of them, the slope of adiabatic process is equal to gamma times slope of isothermal process. And anyway, gamma is always more than 1. So slope of adiabatic process is always more than slope of isothermal process. So we can plot a graph. So this is a isothermal expansion. It's an adiabatic expansion between two same volumes. So let me take volume V1. This value, let me take as a volume V2. So gas is going from volume V1 to V2, but under two different processes, and the PV graph has a different slope. And since it has a different slope, the graphs are having different slopes. But what is asked is the work done. You have to find out in which case work done will be more. So we know that work done is simply area under PV graph. Area under PV graph. Now look at the adiabatic curve. The area below adiabatic curve is less, and area below the isothermal curve is more. That means work done in isothermal process will be more than work done under adiabatic process. So therefore, work done in isothermal process will be more than work done in a adiabatic process. Question 25. 1 mole of an ideal gas at an initial temperature of T Kelvin does 6 R joules of work adiabatically. If the ratio of specific heats of this gas at constant pressure and at constant volume is 5/3, the final temperature of the gas will be. So gas undergoes a adiabatic process, and something is given related to work done. So let's use the equation of a adiabatic process for work done. So W is equal to R into T initial minus T final. So work done is already given as a 6R. R as it is. Initial temperature, let me take as a T. Final temperature TF. This gamma value is given here, 5/3 minus 1. Let's solve this. So this can be written R T minus TF divided by 5/3 minus 1. This becomes a 2 divided by 3. So let's take it to the other side. So 6R into 2/3. Take this quantity to the left hand side. That is equal to R into T minus TF. So R cancels on both the sides. So this is 12 by 3, that will be 4, is equal to T minus TF. So TF, take it to the other side and take 4 to the right hand side, T minus 4. This will be the right option, that is option D. Question 26. A Carnot engine has the same efficiency between 800 Kelvin and 500 Kelvin and X Kelvin and 600 Kelvin. The value of X is. Let's use the equation of efficiency. Efficiency of engine, that is 1 minus T2 divided by T1, where T2 is nothing but temperature of the low reservoir. We also call it as a sink, and T1 is a temperature of the high temperature reservoir. We also call as a source. So T2 is always less and T1 is always more. Now, if you look at this set, for this set of temperatures, 800 Kelvin is T1, 500 Kelvin is T2. Similarly, if you look at this set of temperature, so here X Kelvin is T1, this will be T2. So what is given is efficiency in both set of temperatures is given same. So in the first case, let's use 1 minus T2 500, 800. So that becomes 3 by 8. In the second case, once again, let's use the same equation here. So 1 minus 600 divided by X. But what is given is efficiency in both cases given same. So therefore, we'll equate this equation 1 with the equation 2. And let's solve that equation. So we have 600 by X, 1 minus 3 by 8. So 600 divided by X, this is equal to, this becomes 5 divided by 8. So let's solve X. X can be written as 600 into 8 divided by 5. So this is going to become equal to 960 Kelvin. 960 Kelvin, that is option B. Question 27. A cyclic process ABCA is shown in the VT diagram. The same process on the PV diagram is. Now look at this graph here. From A to B. A to B, the relation between volume and temperature is linear. So let me show one more slide. So A to B, the relation between volume and temperature is linear. That means if V is proportional to T, this implies that pressure is equal to constant. From A to B, the pressure must be constant. So we can rule out option D. Pressure is not constant, but in all other options, first option A to B here. So A to B, we can rule out option B also. Pressure is not constant there. But in first option, A to B, pressure is constant. In second option also, A to B, pressure is a constant. So both options are possible now. Let's look at the part here, B to C. So from B to C, look at the graph from B to C. From B to C, the volume is constant here. We have to identify which option is possible. So from B to C, in both option C as well as the option A, volume is constant. So both are possible. And coming to the last part, that is C to A. From C to A, temperature is constant. So if temperature is constant, so we have to identify the relation between pressure now. Look at the given graph here. When the gas goes from C to A, the temperature has become constant. It's a isothermal process. So if temperature is constant, then pressure will be proportional to 1 by V. So the relation between pressure and volume must be a hyperbola. It must be hyperbola from C to A. Now look at option A. In option A, C to A, there is a straight line. This option is not possible. And if you look at option C here, the relation between A to C is a hyperbola. This is the right option, which represents the isothermal process from A to C. Question number 28. The third operation involved in a Carnot cycle is. So if I plot a graph of pressure versus volume, we all know that there are 4 steps in Carnot cycle. The first one is called as a isothermal expansion. The second one represents adiabatic expansion. Third one represents isothermal compression, and the last step represents a adiabatic compression. So in the question, what is asked is a third step. So third step must be isothermal compression. That is option C. Question 29. 1 mole of a perfect gas in a cylinder fitted with a piston has a pressure T, volume V, and temperature T. If the temperature is increased by 1 Kelvin, keeping pressure constant, the increase in volume is. Let's use the ideal gas equation. We have PV is equal to sum RT. So we don't know any initial conditions, but only thing that we know is a pressure is kept constant. So if the pressure is kept constant, volume will be proportional to temperature. So we can write V1 or V2 by V1. This can be written as a T2 divided by T1. So V2 as it is, let me write V1 as some initial volume V. On the other side, we don't know anything about the temperature. So let me just assume that initial temperature is 0 degrees Celsius. So if it is 0 degrees Celsius, this will be 273. And now final temperature is increased just by 1 Kelvin. That means it must be 274. It is increased by 1 Kelvin compared to the initial. So therefore, final volume V2 has become now equal to 274 divided by 273 times the initial volume. But what is asked is a increase. There is a word here. It is an increase in volume. You have to find out the change in volume, delta V. So that is equal to V2 minus V1. That becomes 274 divided by 273 V1 minus V1. So that becomes a V divided by 273. That gives a option C as a correct option. Question 30. In the following indicator diagram, the net amount of work done will be. Now look at the process here. The first process is a cyclic process, but it is in clockwise direction. And look at the second process, it is also a cyclic process, but it is in a anti-clockwise direction. And we already know that work is always equal to area enclosed by the PV graph. So if you look at the first process, area enclosed by the first process is lesser, area enclosed by the second process will be more. And since first one is a cyclic, this work done is positive, and work done in the second process, which is anti-clockwise, work done is negative. And since second area is more than first area, the net work done also will be negative. That gives us option second as a right option. Thank you, everyone.